Hey there guys, so I'm going to be discussing the solution to problem of the day 291, and I wanted to do a video solution because I wanted to do this at least once in my lifetime, and it's just a pretty fun problem to try to make a solution out of. So anyways, I'm going to read the problem statement and then discuss any assumptions that we're making throughout the problem, and then we can try to solve it in a step-by-step process. So, a plasma gun can fire a beam of plasma that has a uniform velocity distribution in the interval of v and v plus delta v. The barrel has a cross-sectional area as S and initial kinetic energy E sub 0, and the plasma pulse takes an infinitesimally short time to fire. So, let's step back. I said that it's moving in an interval of v and v plus delta v. And the particles, we're going to assume that they're moving in one direction, and you can see the velocity interval, and the difference between the minimum and the maximum is delta v. So also, when I say infinitesimally short time to fire, I'm going to say that the recoil time is very small, so you can replace the differential delta t with dt. So we're assuming that we want to fire this plasma gun at some people who are spam pinging you in Discord, just like this guy who is spam pinging me multiple times, and we want to fire this gun, which the particles that are traveling at the person carry a heat flow of Q, and the skin can cool off this heat flow, and we want to know the minimum distance the person can stand without getting hurt by the plasma gun. So basically, the point of time where the skin is able to cool off the plasma, the heat flowing into the plasma enough so that there's going to be equilibrium, essentially. So what that tells us is that we might want to discuss or discover how the relationship between power and energy is. This is because that P, the power, can be expressed as dq over dt, where Q is the heat. And in this problem, we're saying heat flow Q, and that means that we're expressing as per unit time times area, per unit time per unit area. So that means that in this problem we can write the power flow as Qs, and that's great. And another thing that we might want to know is that power can be written as change in energy over time. So we might want to find the total kinetic energy in another way, and that's what we're going to try to do at the moment by considering small delta v sections. So note that kinetic energy is proportional to v squared, right? So if you consider a section delta v, the kinetic energy can be written in this way, where k is a constant, v squared times delta v, where delta v is all the particles in that section. So if delta v is very small, we can write this as a differential. dE sub k is equal to kv squared dv. So if we integrate this from a velocity distribution of VO and VO plus delta V, we can write something like this. So we're integrating from bounds dE sub k. I hope that makes sense from what we did. And by replacing what you got for dE, we have kv squared dv. And note that this integral by power rule can be written as 1/3 kV to the power 3. And by integrating from bounds of VO plus delta V and VO, we can say that it is also, in other words, K over 3 times VO plus delta V to the power 3 minus VO cubed. Since we don't know what K is, we can go ahead and write this as K is equal to 3 sub 0 over VO plus delta V to the power 3 minus VO cubed. Alright, that's pretty solid start so far. So now let's consider again the change in velocity. So the particles, let's consider a time delta t that on the particles that hit the person. So initially there are going to be some particles that arrive to the person at a time t minus delta v, where delta t is the time from the particles initially hitting the person and the time of the last particles hitting the person. So these particles hit at a time t minus delta t, and these particles hit at a time t. So we can say that because of this, VO plus delta V is equal to x over t minus delta t. And if we subtract both sides by VO, we can get that delta V is equal to x over t minus delta t minus VO. And VO can be written as also as x over t. So substituting this in, we can see that it is equal to x over t minus delta t minus x over t. In collective as one fraction, this can be written as x times delta t over t times t minus delta t. So now, again, we said that delta t is infinitesimal. So what that means is that delta t goes to dt. So at the bottom, so if you replace the differentials like this, dv is equal to x dt over t times t minus dt. Note that this can be written as just t or approximately t because dt is very small and subtracting by differential is approximately the same. So this can be written as x over dt and x times dt over t squared. Alright, so remember power is written as the derivative or rate of change of kinetic energy per unit time, and by substituting this in from our formula for energy, which is kV squared dV, we can say that dV dt. We know that dV is equal to x times dt over t squared. So it is equal to kV cubed over kV cubed x over dV equal to, over t squared, which can be written as kV to the power 4 over x. Alright, so that's pretty awesome. Now we can go back and replace, but first note that the maximum power will be when V is equal to VO plus delta V. So power at maximum is KVO plus delta V to to the power 4 over x. And note that if you're confused why we change from time to only in terms of x and v, it's because we don't want time in our answer. So that's why. And note that we are substituted by taking into account that v is equal to x or t. So now we can equate the power. We got qs from what we discussed back here, and we have p max here. So that's awesome. Now we know that k, we solved for k to be 3e sub 0 over VO plus delta V to the power 3 minus VO to the power 3. So by placing the k here, we get get this. And this is awesome because now we have everything in a linear relationship, and now we can just replace, cross multiply, and we get that x is equal to 3e sub 0 over qs times VO plus delta V to the power of 4 over VO plus delta V to the power of 3 and VO minus VO to the power of 3. So this is our answer. So that was a pretty fun problem, and I hope you guys enjoyed it. And remember that I forgot to say this, but we assume that the effects of gravity could be neglected, assuming that t is very small and the particles don't fall down. So anyway, so thanks for watching, and yeah, bye guys.